Okay, good. All right, good morning, everybody. You're gonna have another talk on this model, but the last one. And we're gonna be talking about desirable energy generation in this Vibro Impact Energy Harvester device. But now we're actually gonna think about dry friction and how that affects the dynamics, the bifurcations we see, and of course, energy. And so again, this is the usual device. You've seen it already many times. There is a capsule that's like externally driven and a ball inside that capsule that's moving. The ball can impact at the ends of the capsule. They are made of these dielectric membranes. We can convert energy from the impacts to electrical energy, and we can harvest that energy to power all these devices that Daniel, Dimitri, all of us have been talking about. And just for notation, we're going to have the lowercase m and x representing the mass and displacement of the ball, the smaller mass. The capital letters will correspond to the capsule. Beta is going to be our angle of inclination. S is the length of the capsule. And again, we have that periodic forcing. And again, there has been a lot of work done to understand the dynamics of this system, again, in the absence of dry friction. So what do we want to do? We want to consider the effect of dry friction between the ball and the capsule, because that actually exists, right? And it's going to affect what we see. And we want to understand how it affects the dynamics, the bifurcations, the energy, and could it potentially be even beneficial for energy harvesting? We're going to see then. And we're going to do also a comparison between high and low frequency regimes just to see how all of that is affecting our system performance. And so the only thing that's going to change in the schematic now is that I'm going to have this extra force over here opposing the motion of the ball. I'm also going to elongate the ball a little bit. I'm going to turn it into a little bullet so that I don't have to worry about the rolling of the ball for now. So this is what we have been focusing on. So the equations are going to look very similar to what you've seen. So before, you just had this for the motion of the capsule, this for the motion of the ball, which was just influenced by gravity. But again, now we're going to have that friction component. There's going to be an impact condition when we hit the ends of the capsule over here. And restitution coefficient over here will tell us how much velocity we're going to lose after the impact. Also, we're thinking that the ball is much smaller than or less heavy, I guess, than the capsule. So that gives us a simpler impact condition over here. We're going to turn everything to a non-dimensional form so that we have fewer parameters to worry about. And this parameter D, you've seen it a few times, is what we want to keep track of because it's actually a combination of a lot of physical parameters. It depends on the mass of the capsule, the frequency and amplitude of our forcing, and the length of the capsule. And I'm going to turn everything into the relative frame. So again, that we have fewer variables to worry about as well. But remember, now we have this force, this extra dry friction force that actually opposes the motion of the ball, and it's going to change direction based on the relative velocity. So when z dot is positive, which is my relative velocity, we're going to follow this differential equation, which is cosine essentially minus this constant and L plus. But when the velocity is negative, our constant is going to change. So that says that, yes, we have the impacting dynamics that we also before. So when we hit the ends of the capsule, but now we're also going to have to worry about this Filipov dynamics that happen when you actually cross z dot equals 0, when your relative velocity becomes 0. And so we're going to be thinking about these ends as the impacting surfaces, and I'm going to call this z dot equals 0 boundary or switching boundary sigma. So what's going on when we intersect sigma is going to be something to be thinking about. And in the phase plane, just to give you an idea, we're moving clockwise in the phase plane, so we're going to see a few pictures like that. Okay, so what can happen now that we have dry friction? What is it to think about? Well, our ball can, let's say we're starting at the bottom, our trajectory can start moving up, and now it's time to interact with sigma. So what's going to happen? Well, the simplest thing is that we can just cross. That's fine when this condition is satisfied. So basically, we solve our our dynamical system at the bottom, we solve our dynamical system at the top, and we concatenate the solutions, and that's all fine. Or we can have sliding now, where the ball and the capsule are moving together for a while. And so again, we can have conditions based on the flow and how the flow points towards that switching boundary that can tell us when sliding can happen. And from those conditions, we can predict when sliding can happen. We can actually calculate how long it's going to last. So we actually have a lot of information about that sliding interval and how it will depend on the various parameters that show up in this L plus and L minus. Okay. So there has been a lot of work done. This is just some of it regarding these conditions for sliding, non-stick motion, and so on, based on properties of the flow, the directions of the flow, just to say, okay, what are possible motions that you can see in the system? Usually it's mostly in horizontal impact pairs. There's, of course, numerical work that has been done with drive friction and other things. We're going to put all of that together, essentially. We're going to think about these conditions that predict sliding motions. We're going to think about maps that capture these motions, and we're going to think about bifurcation and energy, all of that together. So let's see what our typical bifurcation sequences. Rachel already showed a little bit of that because this is the case where there's no friction. So we can start with a 1-1 motion. So I have everything very color coded. So blue is going to be an impact at the bottom membrane. Green is going to be an impact at the top. And so you see here at high values of D, we have 1 dot at the top, at the bottom, 1 dot at the top membrane, bottom of the picture. And so this is our 1-1 motion. We go into a period doubling bifurcation and a little bit of chaotic here behavior. But then eventually this gamma plus shows a grazing bifurcation on at the bottom membrane, which actually is going to introduce a new impact. And that kind of grazing bifurcation is exactly what gives us that reduction in the energy. So we're going to stay, all of us have been saying this 1-1 motion is actually the desirable motion for energy harvesting. So as we start increasing the friction, I'm going to start playing with that mu k a little bit. For small mu, the qualitative picture seems very similar. But as we make that mu a little bigger, we see that, okay, we had a period doubling bifurcation, but then forget about the sigmas for just a second. That period doubling branch sort of closes. We go back into a 1-1. Then there is a new period doubling bifurcation towards the end, and then the regular grazing at the very end. And similar with even higher friction, we also see that there is a cleaner picture towards the end of that 1-1 branch. So that kind of chaotic behavior has kind of vanished, and we see some cleaner period doubling there. There's some part of mine. There are more dots here. I don't know why. Okay. But now these sigmas that I'm pointing here are showing the fact that this kind of qualitative change in the bifurcation diagram is because now we're starting to interact with that sigma boundary. There are these sliding motions that start occurring, and they change the qualitative picture in what we see in the bifurcation diagram when we have here this D parameter and our velocities on the y-axis. Okay. So let's focus a little bit here. So I'm just going to show some time traces just to see what's happening in some of these regions. So this value over here of D is somewhere in this first loop in our bifurcation diagram. And it might not be very clear, but this part of the period doubling is below z dot equals 0. But the next period actually crosses z dot equals 0, and we have sliding. So we see, okay, there starts to be some influence in the motion. And this is also over here, basically, again, in the 1-1. Again, there's sliding that can happen in those solutions. Okay, so what we want to do now is find a way to capture all of these types of solutions using nonlinear maps. This is how we can write down, use basically these equations to construct our maps. And there are different components now that will capture the different dynamics that we see. So we have these L's, L plus and L minus, that characterize the vector field at the for z dot positive and z dot negative. And we have this Sj basically that's going to say, okay, If there is no sliding happening, basically go ahead and integrate your equations of motion. You should get how you evolve from one time point to the next. If there is sliding though happening, you're sticking at the same position at the same velocity, so you shouldn't integrate, you should stay at where you are. And before all of the discussion that Rachel and Daniel showed, we basically cared about a couple of maps, basically from top to bottom, bottom to top, or maybe bottom to bottom if you care about a 2-1 behavior. Here we're gonna care about more maps because we wanna think about all these intermediate behaviors that could happen when you hit sigma. If we go to sigma and then you have to decide, you have to embed those conditions about crossing and sliding and think, am I gonna cross? Am I gonna slide? And so we have all these collections or all these maps. And when you compose them properly, you can get all sorts of behaviors when you try to describe the alternating impacts. So all the different colors actually here, this is the same bifurcation diagram as before for the highest value of mu that I was showing, but all the different colors actually correspond to different types of solutions that came from different combinations of those maps. And so maybe let's look at them a little bit closer, now have them labeled. So we start with a regular 1-1, and what I mean here is the one that doesn't reach sigma at all. So there's nothing, there's no crossing, no sliding. We have a regular period doubling solution. Again, no interaction with that sigma switching boundary at all. But when we go to green, now we start interacting with sigma. Now we start having sliding, maybe sliding and crossing, maybe just crossing. All of that is captured in the green because I was running out of colors. But then eventually we go back to these 1-1 behaviors that again may show crossing or sliding behaviors. But all our maps you see, basically these are from using MATLAB to solve very concrete analytical systems of equations, and you can see how well they overlap with the numerics. So we actually use these maps to capture all of that. And if I zoom in just in this box a little more, so this is the end of that first period doubling bifurcation that goes back into a regular 1-1. You can look even, zoom in a little more and see all the classical bifurcations that show up: grazing, sliding, switching, sliding, crossing, sliding. I have them all sort of labeled here. But basically, you see all these sequences happening and giving you all these different types of solutions and behavior. Okay, so there are all these non-smooth bifurcations that happen on this switching boundary sigma. But we can also do regular stability analysis, linear stability analysis to capture, for example, period doubling solutions, or also to just see when we actually lose stability of those types of solutions. I'm showing the simplest here, the 1-1 that has no sliding, no crossing, doesn't interact with sigma at all. So you can see when I have these thicker circles, it's when our eigenvalues are both less than 1. But then, okay, we cross 1, we have our period doubling bifurcation, they become unstable. And here, once I'm done with the circles and I start plotting dashed lines, it's because we had a grazing sliding bifurcation. So this is now a bifurcation due to an interaction with sigma. And those solutions now become unfeasible. It tells me, okay, those solutions are not feasible anymore. But so we have this analytical framework, we have these maps, a lot of maps actually to capture all of that. We can capture both the sliding and grazing bifurcations and smooth bifurcations like period doubling from all this analysis. But at the end of the day, okay, the application question is what happens with the energy? How bad is it that we added friction to the system? So we have a few different measures. We can measure the energy at an impact at the bottom or at an impact at the top. So again, these are going to be my blue and green lines. But let's think about an average per impact. So that's going to be the red in between. Again, these are the same values of mu that I was showing earlier. But let's focus on the red curves just for a second. So red curves, the pink one, hopefully that's visible enough. The pink diamond is when there is no friction in the system. And as the red gets darker, we add more friction. And so if we focus here around the highest value, D, we see something not surprising. So as we increase the friction, the energy drops, we get a lower value of energy, except especially for the highest value of friction. But then I actually want to focus close to the bifurcation that's happening. So remember that this is the 1-1 branch. Maybe there was some chaotic behavior towards the end, but this jump that happens from this point when mu is equal to 0 to here is because there was a grazing bifurcation that introduced an extra impact, and so we moved to a 2-1 solution, and that dropped the energy. And so the in the case where there is no friction, so again the pink diamond, maybe that bifurcation happens just above 1-1. But the interesting thing is that as we increase the friction coefficient value, that branch of the 1-1 solution actually keeps extending for lower values of these. So we can actually maintain higher energy for lower values of this parameter D, which again depends on the frequency, maybe the amplitude of our forcing, the length, and the mass of the capsule. So this was a very interesting result that friction can actually help a little bit with the energy aspect of this work. So I'm going to move to lower frequency regimes for just a little bit. How much time do I have? Just okay. So this was all before with I was using omega to be 5 pi. So I'm now going to move to a little bit smaller frequency, and that has been motivated from the experiments that Daniel and his postdoc Hendrik have been doing, just to see how things are changing. I mean, typically we see similar things, so similar bifurcations and similar sequences, maybe a few more interesting behaviors. But one thing that happens here in the smaller frequency regime, and especially as we increase the value of the friction, is that we start seeing these non-impacting solutions. So this over here. So you see there are no green dots here, meaning that our ball maybe bounces a bunch of times at the bottom membrane. So these types of solutions are not really good for energy. And another thing that was interesting, so as we decrease D, okay, eventually we get our 1-1 over here. We go into our period doubling. Again, there might be some chaotic regime, but then we move into this branch, which you might think is a 2-1 solution, but actually, so remember, just before this chaotic part, we were in a period, in a 2T periodic solution, but which impacted on either side every period. As we move, and we are actually, there's going to be a grazing bifurcation that's going to lead to a loss of one impact. So remember, before we were hitting twice on the left, twice on the right. Now we're only hitting once on the left and twice still on the right for the same amount of time. So this is what I'm going to say 1-1-0-1 solution that happens over 2 periods. And this is something that we didn't see in the higher frequency regimes. And again, just to point here, you see this loop here, but presumably there could be also sliding or crossing sliding when you have this type of loop at some point. Okay, so I'm going to look again at the energy that we are producing. And this time we're going to think about 2 measures. So we're going to think about average energy per impact. So that's the red over here, and average per time. And so again, just proof of concept, these non-impacting solutions that we were seeing at the beginning for high values of D are not really great. Once we go into our 1-1 regime, we see that both measures kind of give you the same value, but they're higher. And as you decrease D, which here we are decreasing the length of the capsule, this is how we're doing it, that energy starts to drop with decreasing S. So, and then we go into the yellow box, which was giving us this 1-1-0-1 solution. And it's interesting here that the 2 measures are actually different. And so you could assume here that if you continued the 1-1 solution, presumably the energy would continue somewhere here, maybe. But now with this new solution, the average energy per impact is actually higher, but the average energy per time is lower. So depending on what you care about, do you care about this measure or this measure, that type of solution could be desirable or not. So this is what we kind of want to keep track of. And so I'm just going to show very briefly that for different values of restitution coefficients, even though you might not see this type of solution in your numerics, analytically, we again can introduce our maps to find those solutions, maybe for smaller parameter regimes. So this is for higher restitution coefficient. And what I want to point out a little bit here is that, just to finish up, is that, again, our analytics, first of all, help us see if we can extend the desirable solutions past for bigger values of D. So here's the case where R was small, it was 0.3, and we were getting those non-impacting solutions, but I can actually find 1,1 from my analytics, which is over here. But if I choose one of those D values where both of these solutions are possible, and I did 500 simulations from random initial conditions just to see, okay, how often do you land on one versus the other? Actually, the one that doesn't impact is way more frequent. So that's not great. There are not many initial values. So you have to be really careful about your initial conditions if you want to achieve that solution. I also did the same thing in the higher R case where we were finding both some type of 1,1 and this 1,101 solution. And again, with 500 simulations, that 1,101 solution was more frequent, but the 1,1 was also happening in Athens, maybe 200 times out of 500 times. So again, this shows that depending on the initial conditions, we might run into one or the other, and one might be more desirable than the other. So I just want to conclude, say, okay, we have all these conditions, we have our maps, we embed those conditions for sliding and crossing in our maps to get the full picture, and we have that framework to understand the stability, the bifurcations that can happen. The interesting thing is that increasing the friction actually delays the bifurcations, and we can stay in that 1,1 regime for a bit longer, which was kind of interesting. And we get these new types of solutions in the lower frequency regime, which again, maybe are beneficial for us. But we want to think about noise, more perturbations, more things that can change in the future. And again, thanks to Rachel and Daniel and our